Hello everyone, this is Hossein Mohit. Welcome to Relational Data Model video lecture. In this lecture, you will learn about the basics of the relational data model and its tenets, including the normalizational process. Like the previous lecture, this will be a brief summary. So to fully master these concepts, you need to read the textbook and complete the assignments and quizzes. The relational database concepts was first introduced in early 1970s. Before this logical design existed, data management was handled through the physical features. In other words, you had to specify the exact physical address of the data on some, for example, hard disk in order to access, write, read, and modify the data. The relational model brought a revolution in database technology, making it much easier to design and implement databases. The term relation comes from the mathematics and represent a simple two-dimensional table. As you have learned in the previous lectures, relation is another term for the table, entity, or class. Each column in a relation is called an attribute, and each column has a name. This is the attribute name. A set of possible values that an attribute can have is called a domain. We also refer to these as an attributes range or variable range as well. Each row in a relation or table is also called a tuple. Within this context, it is important to remember that a null value is not the same as the zero value. It's a blank value, meaning no value exists. It represents non-existence. Additionally, an essential concept in relational database is concept of keys, which we will discuss in more detail in a future slide. So we have two kinds of keys. One of them is the primary key and the other one is the foreign key. Each table or relation in a relational data design needs to have a primary key. Before identifying the primary key, you first need to identify the candidate keys. A candidate key is any attribute within your relation that can uniquely identify a row in that relation. Essentially, a candidate key is an attribute that has a unique value for each row. The primary key is the candidate key you choose to be a unique identifier for that relation or table. It can be a single attribute or even composed of multiple attributes. So when two or more attributes works together to ensure uniqueness for identifying each row, you have a composite primary key. Within the primary key concept, you might also come across something called a surrogate key. A surrogate key is typically an automatically generated primary key with no meaning outside of the system. In the past, surrogate keys weren't very popular, but now with the cheaper storage and computational cost, they have become the most common and de facto standard in the database design. For example, student IDs or course IDs are generated IDs that have no meaning beyond identifying in a specific record within a table. Additionally, you may encounter something called an external key. An external key is a primary key that has a real world meaning, such as social security number. Social security numbers, which are meant to be unique, were frequently used as a primary keys in the past, especially in the 70s and 80s. However, they are not used as a primary key as much today. Next is the foreign key. A foreign key is the primary key attribute from one relation that exists in another relation. Sometimes it can exist even within the same relation, which we call recursive relation. You will learn about this one in the future later. Generally, a foreign key in one table is a primary key in another table. The foreign key functions as the foreign key functions as a connector between two tables, enabling you to write queries and create database schema. One important note to remember is that the foreign key must always refer to a full primary key. If your primary key is a composite key, meaning it has multiple columns, and you want to use it as a foreign key in another table, you need to include all the columns from the composite key. For example, if your composite key has more than one column, for example, two columns, all those columns need to be used as a foreign key in the other table. In this example, as you see, when we have the student ID for the student table and course ID for the course table, in the grade in course table, you need both a student ID and course ID to accurately assign grades to students for each course. Therefore, both a student ID and course ID become foreign keys within the grade in course table. And together, they also form a primary key for the table. Now, for the relational design and relational model to work flawlessly as intended, there are some integrity concentrate that need to be applied and consistently monitored when designing a relational database. These are entity integrity and referential integrity constraints, which you need to ensure are met during the design and implementation process. So the first one, the entity integrity. This rule states that no key attributes of any row in a relation may be null. Essentially, you cannot have null values within your candidate key, or certainly no null values within the primary key. The other rule, the referential integrity rule, on the other hand, states that every foreign key must either be null or its value must be an actual value of a key in the referenced relation. Referential integrity applies only to foreign keys, and it implies that the value in a foreign key field must point to an actual row in the reference table where this foreign key is a primary key, or it must be empty or null value. A foreign key value cannot point to something that does not exist. So one more time, a foreign key value cannot point to something that doesn't exist. So how can these referential integrity violation happen? Let's look at these examples. So in the first example, the first table, as you see, so you can see that the entity integrity is being violated. This happens because we have no values within our composite primary key, which consists of both a student ID and course ID. So as you can see here, so we don't have value for both of these values. And regarding the referential integrity, this can be violated. For instance, one of the course ID, let's take course number 8 as an example. So you can see the course number 8 here as an example, does not exist in the actual course table. So let me go back to the previous slide. So we can see that in this table, there is no course ID 87756. Okay. So the course ID 8 does not exist in this table. So this might be due to the fact that, for example, student 1 had taken course number 8 at one point, but the school or institution later decided to delete that course. But since course number 8 are no longer exist, this creates a referential integrity violation. This type of violation cannot happen in a properly functioning relational database. The relational model enforces that entity integrity and referential integrity must be maintained. To reduce the chance of integrity violation or to completely eliminate them, we need to go through a process called normalization. Normalization essentially recognizes your data and database schema in a structured way that eliminate the chances for common errors, such as insertion anomalies, deletion anomalies, and update anomalies. To ensure that no anomalies occur and also integrity concentrates are always enforced, the normalization process is crucial as important. This process is based on the concept called functional dependency. Functional dependency means that the value of one attribute are dependent on the value of another attribute. In other words, one attribute determines the value of another. For example, the value in the student ID field determines the student name, address, status, and other related attributes. In this case, we say that a student name is functionally dependent on a student ID, or a student ID functionally determines the student name. So to begin the normalization process, you first need to identify all the functional dependencies within your table or relations. Once all these dependencies are identified, you can start normalization process to further organize the data and eliminate potential anomalies. There are four normal forms in a database design, with three of them being absolutely essential. You always need to ensure that your database schema is at least in the third normal form or 3NF. A relation, let's first start with the first normal form, which we call it as a 1NF. A relation is the first normal form if all values in the relation are atomic. This means that each attribute must have a single indivisible value. No attribute can contain a set of values or repeating groups. Essentially, the first normal form requires that every attribute in each record or tuple has only one value. In a simpler terms, for any row in your table, no column should have more than one value. Simple. The second one, second normal form or 2NF. The second normal form builds on first normal forms. It states that no non-key attributes, a regular attribute that is not part of the primary key, should be functionally dependent on just part of the composite primary key. This is a particularly important when you are using composite primary key, which one that consists of more than one attributes. In a second normal form, every non-key attribute must be fully and completely dependent on the entire primary key, not just part of it. And the third one, the third normal form, 3NF, the third normal form takes things a step further. It requires that for every functional dependency where attribute X determines attribute Y, X should be a candidate key for that relation. This means that if an attribute is determining the value of another attribute, it must be a candidate key for a primary key within that table. I will discuss these normal forms in more details along with example in the next slides. So in the first example at the top left, we can see a violation of the first normal form. Look at the skills column. Each employee can have more than one skill, which violate first normal form. According to the one normal form or first normal form, each attribute must have an atomic value, meaning that in a given row, an attribute cannot hold multiple values. For example, in the first row, the skill attributes has two values, programming and query optimization. To fix this and bring this table to the first normal form, you need to create a new table. This new table will have a composite primary key, which consists of the employee ID and a skill attribute. By doing this, you remove the multi-valued attribute from the original table. So if you want to convert the employee table to the first normal form, you will have two tables. The first table, employee table, contain attributes like employee ID and employee name. The second table, which we call it a skills table, contains two columns, employee ID, which links the skill to the employee, and a skill, which each skill will have a separate row. For example, employee 101 would have two rows, one with 101 programming, and the other one is going to be 101 query optimization. The combination of the employee ID and skill forms the composite primary key in the new table. Let's move to the second normal form. For the table to be in a second normal form, it must first satisfy first normal form, meaning all values are atomic and there are no repeating groups. Additionally, second normal form required that all non-key attributes are fully dependent on the entire primary key. If your primary key is a composite key, meaning it consists of more than one attribute, each non-key attribute must depend on all part of the composite key, not just subset of it. So, however, the second normal form violation can also occur in tables within a single attribute primary key if there are functional dependencies that aren't fully dependent on the primary key. For example, in the grade in course table, the composite primary key consists of both a student ID and course ID. The issue here is that the student name attribute is dependent only on a student ID, not on the entire composite key, both a student ID and course ID. This creates the second normal form violation, as the student name doesn't depend on the full primary key. So this violation of the second normal form leads to have some problem for us. The first one, redundancy. For example, the name Emery Smith appears multiple times in the table. So if, for example, we had more data, this redundancy would consume unnecessary storage and computational resources. The second one, data integrity issues. With redundancy, there is a higher risk of data becoming inconsistent. For instance, if Mary Smith's name is entered incorrectly, it would need to be updated in every occurrence, making maintenance difficult. To resolve this second normal form violation, we need to create a new table that uses the partial key attributes, in this case, a student ID, as the primary key for the new table. So to fix this uh, grading course table, you would create a new student table that uses a student ID as the primary key and includes attributes like student name that depends on it. Also, remove the student's name from the grading course table and store it in the student table. So you would repeat this process for all violation in the table to ensure it is in the second normal form. So let's talk about the third normal form and why it is important in a database design. So to really understand this, let's consider a relationship between the non-key attributes. So the rule with the third normal form is simple. One non-key attribute should never depend on another non-key attributes. If that happens, we have a problem. Let's this one as an example. Uh, Imagine you have a bank name and bank routing number in the same table. Now we know that the bank routing number uniquely identify the bank name, right? If you keep both attributes in the same table and neither of them is a primary key, you would violate the third normal form. Why? Because bank name is dependent on bank routing number and neither is a key in the table. So one of these attributes need to be primary key, or you should split them into different tables. Let's have another example. Imagine an employee table where we have three columns: employee ID, skill type, and bonus rate. Seems simple enough, am I right? But there is a hidden issue. Here is how the data works. Employee ID tells us about the skill type of the employee and also tells us about the bonus rate. But wait, there is another dependency. A skill type determines the bonus rate as well. Now, this is where the problem starts. A skill type is not a candidate key for the employee table because it is not unique. Multiple employees can have the same skills. So because a skill type isn't unique, it cannot be candidate for the primary key. And because a skill type determines bonus rate, we have a functional dependency problem between the two non-key attributes. This is exactly what third normal form tell us to avoid. So how we can fix this? We need to break this table down to the two tables to remove this violation. Here is what we need to do. We create a new table called a skill. This new table will have a skill type as the primary key, and it will store the bonus rate associated with each skill. Now, in the original employee table, we need to remove the bonus rate and just keep employee ID and a skill type. We will use skill type as a foreign key to link employee table with the new skill table. So this a simple change put both tables into the third normal form, which eliminates the dependency problem. So you should always aim for the third normal form from the start of the designing process. If your table is in the third normal form, you can assume that it is already in the second and the first normal form as well. So here is an easy way to summarize the first, second, and third normal form in one sentence. All attributes in a relation must depend on the key. That's the first normal form. They must depend on the whole key. That's the second normal form. And they must depend on nothing but the key. That's the third normal form. So remember, all attributes in one table must depend on the key, the whole key, and nothing but the key. If you follow this rule, your design and tables will be in the third normal form. And finally, the fourth normal form. A relation is in a fourth normal form if it is already in the third normal form and has no multi-value dependency. So what do we mean by multi-value dependency? So let's go through the example to make it clearer. Imagine we have a faculty table that include committee and the course assignment for each faculty member. So you can see that the faculty member's name being repeated. For instance, Jones appeared twice, once as a part of the admission committee and again for the course IM 101. The same faculty member might be part of another committee or be assigned to a same course again. To record all the combination of the committee, faculty, and the course assignment, we are repeating this data. However, there is a better way to design this so that we don't have to repeat the data and avoid multi-valued dependency. So instead of having just one faculty table, we can create two tables. One for faculty and the other, one for faculty and committee assignments and the other for faculty and course assignments. In the faculty and committee assignments, we would store faculty name and committee assignments. In the faculty and course table, we would store faculty name and course assignment. In both of these new tables, the combination columns or the combination of the attributes would form the composite primary key. So the ultimate goal of fourth normal form is to reduce data redundancy and ensure that no insertion or update anomalies could occur because of these redundancy. So that was a quick review of the fundamental concepts in a relational database design. So you have learned about the key concepts and the normalization process in this lecture. However, as I always mentioned, and also mentioned at the beginning, these lectures alone isn't enough to ace your quizzes, assignments, or exams. You need to read the textbook and complete the assignments and quizzes in order to be successful in this course. Have a good week.